All right. Well, I'll get started. Excuse me. I'll begin with a word of prayer. So, Heavenly Father, we thank you for the break just completed, and just ask that you just guide our steps today, help us to glorify you what we do, and help the students as they prepare for the soon upcoming test and just finishing their homework and everything, that they would just to make the most of their time and just to glorify you in what they do, Lord. In your name I pray, Lord Jesus. Amen.
Amen.
All right, so I'll get straight into it. I'll talk about graphs of rational functions. So first of all, let me do a kind of fun example. A little bit fun. So, so suppose we want to graph y equals to something like, I don't know, x to the fourth divided by x minus 1. Suppose you wanted to graph this. So how would that go? Well, it goes something like this. First of all, I need to figure out how to divide that into x to the fourth. So I've got an x cubed. That gives me x cubed minus x to the fourth, rather. Minus x
cubed. Polynomial division.
Yeah, and that gives us x cubed. So I get plus x squared. So I have x cubed minus x squared, which gives me x squared, so I get plus x here. Then x squared minus x, so I get x plus 1, so I get x. So I get a remainder of 1. So apparently, this thing is equal to x cubed plus x squared plus x plus 1, all right, plus 1 over x minus 1. Now, so how would we graph this? Like, how would you think about graphing this? Here's how I'd think about it. So what are the features of this graph going to be? So it's going to have a vertical asymptote when x is equal to 1. When x is equal to 1, we have a division by 0. So the formula is going to blow up, all right? But if x is, if the absolute value of x is much, much greater than 0, then 1 over x minus 1 is approximately 0, right? And what do we have? Well, we have y is approximately just x cubed plus, x squared plus x plus 1. But you know what? Really, we just have y is approximately x cubed. In this case, if we're really, really large values of x, yep.
Can you move your computer, please?
There you go. So if we're really, really large values of x, we just have that. So graphically speaking, here's what goes on. To a reasonable approximation, the picture of the graph looks something like this. I have, a vertical asymptote here at x equals to 1. And then, let's see here. Where does it go through? If I plug in 0, where do I get? What's the value of this function when I put in 0?
0.
0, right? So the x-intercept and y-intercept actually is 0 for what it's worth. So it goes through here. And so it's got to look something kind of sort of like this. And then So what I'm trying to graph, and I don't know if I'm doing a very good job here, is essentially the picture is the graph of the, it's essentially the graph of the cubic function, which is something like this. But it's been spoiled by there being a vertical asymptote in here, which just kind of like takes this and like instead of just going like that, it goes like this, and then it goes something like this. So this graph has what's known as a, this graph has a cubic asymptote. Why is it called the cubic asymptote? So, yep. Because this piece right here is a cubic, right? Because after a long time, after large values of x, the graph essentially just looks like a cubic. All right? What other kind of asymptotes could you have? Yeah, Michael?
Horizontal asymptote.
Horizontal asymptotes, right? Like we could have this, example 2. If I had something like this, x squared plus 1 over x minus 1. If I had example 3, if I had something like y is equal to 3x minus 1 plus 2 over x squared. Well, these would also be examples which had interesting asymptotes. Like this, you would have y equals x squared is the asymptote, asymptotically. And this one would have y equals to 3x minus 1 as its asymptote. So example 3 actually would be, it has another name in algebra books. In example 3, you'd call the asymptotes what are called, they'd be called slant asymptotes, because it actually asymptotically goes to like a line, all right? Now, once upon a time, I actually would test on slant asymptotes, but that time is gone. So if I'm not going to test on slant asymptotes, you might guess that I'm not going to test on parabolic asymptotes, right? Which probably means that I'm certainly not going to test on cubic asymptotes. But I think it's good for us to have this discussion to understand like the general idea. The general idea is whenever we have two rational functions, right? If we've got p of x over q of x, the story is this. If the numerator function has larger degree than the denominator function, we do long division, and the part that appears here will be the asymptotic behavior. All right? Now that's actually pretty tough to graph if the numerator has like 3 more degrees than the denominator or something like that. But for us, we're going to focus the rest of our attention on the case that the numerator and the denominator either have equal degrees, or, better yet, the case that the denominator actually has a degree smaller than the numerator. In those cases, the asymptotes are just horizontal asymptote, and it's either going to have the x-axis as the horizontal asymptote, or y equal to a constant, all right? So here's the theorem. If the degree of f of, p of x is less than or equal to the degree of q of x, then y equals to p of x over q of x has, number 1, a horizontal asymptote of y equals to 0, given the degree of q of x is strictly greater than the degree of p of x. All right? Or number 2, and let's not keep writing horizontal asymptote, because like Who wants to write that, right? So let us abbreviate this as HA. Horizontal asymptote of y equals to, let's say, a, goodness gracious, I don't know, a sub n divided by b sub m, where a sub n is leading coefficient for p of x, and b sub m is leading coefficient
Q of X.
for q of x. And the reason this is going to work out this way is essentially just long division. If you look at the formula, so what I'm saying is that in this situation, you've got like y is equal to an x to the n plus dot 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 divided by bm x to the m plus dot 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 dot. And so if we simplify that, we have an plus dot 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 divided by, oh, I'm an idiot. I don't need an m and an n here. We just need n for both. Both of these should be n. Both of these should be n. My bad. The reason for that is that's when this case happens. And so if we could basically just divide, eventually we get to a sub 0, right? Eventually we get to b sub 0 here. And so if I divide the top and the bottom by x sub n, I eventually get like a sub 0 divided by x to the n. And over down here, b sub n plus dot 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 plus b sub 0 divided by x to the n. My point to you is in this formula, everything is like going to 0 except for the leading terms. If you just divide by x to the n, this is approximately equal to a sub n over b sub n for, you know, x going to, let's say, plus or minus infinity. So that's the story. Let me show you some examples of that. All right, so example 4. We'll keep this one nice and simple. Y equals, you know, x over x squared minus 1. Let's talk about how to graph this. How do we graph this? So first thing we do, factor the denominator.
Yep.
Okay, so x over x plus 1 times x minus 1. So I've got critical numbers of 0, minus 1, and 1. Put them on a number line. Minus 1, 0's in the middle, 1's over here. And then just plug in some points for good measure. Let's see here. If I plug in like 3, I get plus, plus, plus. So I start out positive over here. Come on. Man, that one cap really doesn't want to come off. And how about the multiplicities of the factors? What are they? Well, they're 1. Every factor has multiplicity 1. So that means I flip signs at each critical number. So I go plus to minus, and minus to plus, and plus to minus again. All right. Now here's the deal. Whenever I have division by 0, I get a vertical asymptote. So to draw those, I've got vertical asymptote here at 1. Excuse me, minus 1. Vertical asymptote. And also 1 at 1 over here. X equals to 1 vertical asymptote. Now what? What's my horizontal asymptote? Can you guys tell me what's the horizontal asymptote for this one?
So, the horizontal asymptote would be,
I heard a 0. That's right. The reason for that is the degree of the denominator is 2, whereas the degree of the numerator is 1. 2 is bigger than 1, therefore we have case 1, horizontal asymptote of y equal to 0. That means that the graph has to get sucked into the x-axis eventually. So basically, we're looking for long term, the function has to be drawn into this x-axis, right? Y equals to 0 is the horizontal asymptote. What else do I know? I know that 0 is an x-intercept. See that? 0 is the x-intercept again. All right, now I have everything I need to graph. The rules are your function has to blow up to infinity or to minus infinity at vertical asymptotes, and it has to tend to the horizontal asymptote long term. It also has to cross the x-axis wherever you have an x-intercept. Put all that together, respect the sign chart, it has to look like this. So there you go, there's your graph. Just look at that. It's good? Well, anyway, that is how you graph this, okay? So just to review, the steps for graphing a rational function are to factor it, to completely understand how the factorization of the numerator and the denominator is all laid out. Draw a sign chart, all right? Identify what your vertical asymptotes are, right? Identify what the horizontal asymptote is, and then graph. Again, always keeping in mind the sign chart, because we should be plus where it's plus, and we should be minus where it's minus, okay? Example 5. Now there is another wrinkle I haven't gotten to yet, but we're going to start with the easy part. Well, I'm not saying, actually the thing I haven't done yet, it's not really harder, it's just weird. So here's another one. Y equals to, I don't know, how about x squared minus 4 divided by, how about x squared minus 8x plus 7. All right? Now this one, I'll just tell you right off the bat, what's the horizontal asymptote going to be?
X squared.
No.
What's,
We're in case 2, right? The degree of the leading coefficient, what's the leading coefficient here? What?
-4.
Nope. Leading coefficient is 1, and leading coefficient here is also 1. It's extremely silly.
That is a little silly.
All right.
Oh.
Another way to think.
It's on the left side.
Another way to think about this is if x is really, really large, like if you can imagine putting 1,000 into this, does the 4 and the 8 and the 7 matter at all? It doesn't matter a bit. It's completely just 1,000 squared over 1,000 squared, which is 1,000,000 over 1,000,000, which is 1. And the same thing would happen if I put a negative 1,000,000 and like a negative 1,000 in, right? Everything except for the x squareds would be minuscule in comparison. So the horizontal asymptote here, y equals to 1, is the horizontal asymptote. All right, now let's factor this. We've got what? X plus 2, x minus 2, divided by what? X minus 7, x minus 1. We have 4 critical numbers to deal with here. And so I'll put them on my number line. And which one comes first? Going left to right. We got minus 2 is my first contender, right? And then I've got myself, I hit the 1. And then I hit the 2. And then eventually over here I get 7. Right? And then I like to draw my axis under this just to get myself started on the thinking here. Here's my xy axis. I like to draw the graph right under the number line just to make the most use of the number line directly. See how I do that? That's just nice organization for me anyway. And of course, it would be even better if I actually was being more careful with the spacing of the numbers for this particular application. It doesn't matter too much. I'm just trying to sketch the graph. Okay, so, well, let me get the horizontal asymptote out of the way. Horizontal asymptote looks something kind of sort of like this, okay? The graph can cross the horizontal asymptote, that's fine, but the key is that it has to be drawn into it eventually, okay? So, and then the vertical asymptotes here, where are they? Where do vertical asymptotes come from?
The vertical asymptotes come from
The denominator. They come from division by 0. That's why we're getting the formula blowing up, because 1 over a very small number is a big number. So yeah, 1.
So it's 7.
7,
And 1.
7 and 1, that's right. So this is where our horizontal asymptotes, here's where our vertical asymptote's going to be. I usually have some problem on the test
So
where
the horizontal asymptote is in the...
So you usually have some problem on the test where I ask you guys to label the vertical asymptotes, label the horizontal asymptotes, and like sketch the graph. I usually ask one of these questions. I always regret asking it, but I usually ask it because it's never fun to grade. But I do want you guys to learn how to do these things, okay? So now there's like 5 problems in your homework which are about this, so hopefully that gives you practice. And if you look at old tests, you'll see how I've asked this before. But okay, so then what? I need to finish my sign chart. What do I have here? So as is often the case with my stupid formulas, if you plug in a positive number beyond the rightmost critical number, you get?
Positive.
Positive, yeah, plus, 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 plus. If I plug in like 10, I get 8. I mean, I get 12 and 8 and 3 and 9. Those are all positive numbers. I get plus over here. The multiplicity of each one of these factors, again, is 1. So we flip signs. All right. Now we have all that we need, practically, to graph this. When is it crossing the x-axis? There are 2 things that could cross the x-axis at. Either at a vertical asymptote.
Or a horizontal asymptote.
Nope. Or at a 0, an x-intercept of the graph. The x-intercepts are the zeros of the numerator, which here are plus and minus 2. So we go through the x-axis here and also there. All right? Now I have everything I need to graph. So it starts out positive. It gets drawn into that, so it's got to be something like that. And then, it drops down here, like that. Then it's up here again, goes through that x-intercept, gets negative, gets drawn down into that like that. Then it's positive over here, and like that. Now, this isn't quite the right shape, but this is a sketch of what the graph looks like, okay?
Oh, I see.
Michael sees. Does anyone else see? Questions? I feel like there's a question in the corner. Yes.
I'm just like in the middle. I'm trying to figure like how we know exactly how it is.
Well, I don't know exactly how it curves. Like, I could just as well have written something more like this. Like, I don't know exactly. What I know is it's a rough estimate. It cannot cross back across the x-axis. The only place it can cross the x-axis are like these dotted lines where it can jump, or the x-intercepts. That is pretty limiting to what the shape has to look like. But exactly the nature of how this goes down, or is it more like this? You know, is it more like that? Unless what I mean.
So it's more of an overall estimate.
It's a sketch. Yeah, it's a sketch. To fine-tune these graphs and tell you exactly where the lumps are, the things that are beyond where the x-intercepts and the vertical asymptotes are, is to do calculus. Because calculus will reveal where the turning points are, where inflection points are for the graph, things like that. But that, of course, is beyond this course because, well, this is not a course in calculus, right? So, but some of you will take calculus, so you'll learn these things.
Well, I do know that I have statistics.
Statistics, oh, that's too hard for me. I don't want, uh-oh, who's calling me? This is not good. Uh-oh.
How am I doing paying attention?
Oh,
Great, Michael.
oh no. Well, I can't fix it now. Let's see here. All right, so let's look at another example. Let's look at y equals 2 x divided by x cubed minus 9x squared. Okay, yeah, I mean that should be fine. Let's try to graph this. Now this one's going to have a new feature we haven't seen before yet. Something different's going to happen with this one that we haven't quite run into just yet, but we'll get it. All right. So first of all, what's the horizontal asymptote? Horizontal asymptote's like the easiest thing one of the easier things to settle, right? Because you just have to look at it and go, well, if the numerator has smaller degree than the denominator, then the horizontal asymptote's what? Yeah, 0, right?
0.
So this one, we've got degree 1 over degree 3. That tells me immediately the y equals to 0 is the horizontal asymptote. Since, the degree of the denominator is larger, strictly larger. Now, can we factor this? What happens here? We've got what? We've got x over, well, I guess we can do x squared. Oh, man. Sorry, guys. I need to make a slight adjustment here. You'll forgive me. This was supposed to be just x.
Don't worry.
Very good, Michael. Thank you. Michael has the power to forgive mathematical sins.
That's what God told us.
We'll stop right there. So, so x cubed. If I make that an x, then this goes more interestingly, because then that's x squared minus 9. I can factor like that, okay?
Okay.
Then what? Well, I can factor further. To further factor this, I have y is equal to, 1 over, well, that's, x squared minus 9, which of course is 1 over x plus 3 times x minus 3. Now this right here, I need to come up with some labels for things, what's going on. So let's say that the original function was f of x, okay? So here's f of x. This down here is what I usually call f reduced of x. This is only good for x not equal to what?
X is not equal to 0.
X is not equal to 0 is correct. 0 is the one place where I can't do what I did, which was to do what? I canceled the x's. That assumes x is non-zero. So this is the reduced formula for the function for x non-zero. Now if x is non-zero, the formula simplifies like such, right? And then we can graph this pretty easy. Let's do it. Let's do it. Let's see here. So where critical numbers are minus 3 and 3, and the sign chart, pluses over here, minuses up in there, pluses back over here again. All right. Do you guys? I'm doing it for the reduced function, but you could do it for x just the same, I guess. Well, there is something to worry about there. But anyway, okay, great. We know the horizontal asymptote's 0. Let's graph this thing. My y-axis is right in the middle here, like so. My vertical asymptotes are x equals 2, minus 3,
3 and 3.
minus 3 and 3. My horizontal asymptote is the x-axis itself, so that's nice, right? And let's see here, what else? Does this function have any x-intercepts?
0. Only.
But 0 I can't do, because if I plug in 0,
No x-intercepts.
because if I plug in 0, I get 0 over 0, which is undefined. So yeah, 0 is our only hope, but it's not an x-intercept because the function's not defined at 0. What does the graph have to look like? Are you guys ready?
Ready.
Okay.
Oh, just try to stay focused.
Okay, that would be good. So it has to look like this here. And it has to look like this over here. What does it have to do in the middle? It can't cross the x-axis. What does it have to do?
Well,
It has to do what? It has to bow back down, right? It has to go infinite at the vertical asymptote. So it's got to do something like this. It forces us to make this shape. All right, now that's not quite accurate. There is one feature that I have not yet made explicit on this graph, which I would like to add, which is the hole in the graph. The hole in the graph comes from the fact that the formula is not defined at 0. All right? So where is 0? I mean, you can see it. It's about right here, right? But what is the coordinates of that hole in the graph? How do you figure it out? It's going to be at 0. And then what I do is I take the reduced function and I feed it the x coordinate for the hole in the graph. So that's actually what? 0, comma, 1 over 0 squared minus 9, which is also known as minus 1/9. And so there you go. This hole in the graph right there is actually at 0, comma, minus 1/9. So how do we get a hole in the graph? We get a hole in the graph when there is the same factor in the numerator and the denominator, and they just cancel out.
same factor.
Yeah. If you have the same factor in the numerator and the denominator, but there's more of them in the denominator, that gives you a vertical asymptote. If there are more of the factor in the numerator, it puts the hole in the graph on the x-axis, because the reduced function actually would be 0 when you plug in the hole in the graph coordinate. I'll work an example like that next, maybe. Any questions? Yep.
Could you go through how the formula works for plugging in f reduced with the hole in the graph again?
Sure. So what I do is, once I figured out that x is going to be, the same factor top and bottom that cancel out, that tells me hole in the graph. What's left over, I call the reduced function. The reduced function will be defined, because basically the reduced function, you're getting rid of all of the denominator factors for x, okay? So I'm able to plug in 0 into the reduced function. And when I do that, I get 1 over 0 squared minus 9, which is minus 1/9. That tells me that, in fact, that hole is right there. See, because the graph of y equals 1 over x squared minus 9 is exactly what I have in blue with the hole filled in. That's it. That's the logic here. Like, without the stupid multiplication and division by x, the formula is just 1 over y squared minus 9. It's just what I have graphed in blue, again, with the hole filled in.
That makes sense.
In fact, you can take any graph you want, and if you want to just punch a hole in it, it's like a mathematical hole puncher. I'll show you how. It's kind of silly.
Oh, Professor.
Yeah. Yeah, go for it, Michael.
So, F is 0. So to get the bottom, to get the horizontal asymptote, you need to find a hole in the graph.
No, the horizontal asymptote is just from looking at the degree of the numerator versus the degree of the denominator. And if the degree of the numerator is strictly smaller than the degree of the denominator,
Is larger.
then the horizontal asymptote will be 0. If, on the other hand, they match up, then it's the ratio of the leading coefficients. That's the theorem I have on the middle board here. Let me just give you guys a very silly example for a second here, and then we'll get back to the ones with actual formulas.
I still don't get it.
Oh, well, maybe next time. Maybe next one.
But
Let's see here, example
I should
7.
have paid attention.
Well, maybe it'll make sense over here, Michael. So, example 7.
I'll pay attention this time.
Okay. I believe in my heart you were already paying attention. But
I trust you, I'm writing down.
that is good. Me too. Let's see here. I try anyway. Where was I? So make the graph look like whatever you want. All right. I just want it to be a function, so it has to pass the what?
Vertical line test.
Vertical line test. So if my function looks like this, y equals f of x, suppose that's my function. I'm not even giving you the formula for it, right? Suppose I want to have y equals to, I want the same graph, but I just want to punch a hole right here, right? Suppose I want to punch that hole in there right there at 1. How would I do y equals to what? Would put a hole in at 1. What I do is I just take and I multiply by x minus 1 over x minus 1. You know, I just take this function, x minus 1 over x minus 1, which is a very silly function, times f of x. That punches a hole. Like, this is not defined at 1, but otherwise, x minus 1 over x minus 1 is always equal to what? 1, right? So in this silly example, that's how I could punch a hole in 1. I just multiply by this factor, which is undefined at 1, and everywhere else is just 1. That's all that's going on with the hole in the graph, is just these kinds of factors, addressing them. Okay, so let's do another example. I'll try to make the hole land up on the x-axis this time. So example 8 for us. How about this? Y equals to, I don't know, x to the third power divided by x squared minus, my bad, x to the fourth minus 2x, brain not working, third, plus x squared. There, I got it. Yay. Graph this thing. So what happens here? What can you factor out of the denominator? What can you do? Look at this. We've got an x cubed. I can factor an x squared out down there, right? Ah, look at this. So if this is f of x, I can write y is equal to, see, I can reduce the x cubed over x squared and gives me what? Yeah, just a 1x. An x over, x squared minus 2x plus 1. Of course, we can factor that. That's what? X minus 1 quantity squared, right? And this is what I would call the reduced function of x. I've canceled out the matching factors, okay? Where is the hole? I guess all my, I've been kind of boring. It's the same as it's the same as the last example 6. I mean, example before last. Like the hole here was at 0 because I canceled out the factor of x over x. So this one, the hole is again at 0. 0. Because we've got this over that. So there's this formula here.
Because the degree in the denominator is greater than the degree in...
Well, that's a separate issue, Michael. That's for the horizontal asymptote. It is true, though, that the horizontal asymptote would be 0 here because we have a quartic or a degree 4 in the denominator, whereas the numerator is degree 3. Okay, great. Now, what's my sign chart look like? I've got 0, I've got 1, that's it. Now, for the first time today, we finally have a factor with multiplicity 2, right? Multiplicity 2. And let's see, if I plug in a positive number, I get positive, right? But since the x minus 1 factor has multiplicity 2, it bounces, right? But here it's not bouncing off an x-intercept, it's bouncing off an asymptote in some sense. So I go plus, and then I cross at the 0, all right? All right, so let's graph this thing. All right, so I have a vertical asymptote at x equals to 1. My horizontal asymptote, again, kind of boring, but...
X equals 0.
No, easier than that. The horizontal asymptote here is just y equals to 0. And so what's the graph look like? It's like a volcano, right?
Oh, yeah.
It's a volcano. And where...
It goes on both sides.
Right. So where's the hole in the graph this time?
Hole.
So we have 0, comma, f reduced of 0 as it happens. What is that actually, though? What is f reduced to 0? What happens when you plug 0 into this? We get 0. Yeah, it's 0. Yeah, 0. Yeah, exactly. 0 over minus 1 squared, also known as 0. Yeah. So there is a hole in the graph at the origin. Hole in the graph at the origin itself. Little circle right there. And so what the graph has to look like is something like this. It's a volcano. Whee! Right, it's a volcano because we've got that repeated factor there. And then there's a hole in the graph. It comes down here, and then it has to come back up eventually because its horizontal asymptote is y equal to 0. So it's got to look something kind of sort of like that. Any questions? This is pretty much the last really big topic before the test, okay? So I wanted to make sure I gave you guys a good sampling of each one of these kinds of things, and I'm pretty happy with the set of examples I've given you today. For the most part, I was a little bit mean at the start, but let me show you one more example here. Yep.
My example question is going to be, could you do one where the hole's not at 0?
Where the hole's not at 0?
Yeah.
Sure. In fact, this time, I want you guys to tell me the formula, a potential formula for the graph. So let's suppose that we've got a graph that looks something like this. We've got x equals to -1 is a vertical asymptote, and we've got a hole in the graph right here. And let us suppose we've also got an x-intercept here, and it comes back. So let me draw the graph something like this. Sorry if I should have used a different color, my bad. I hope you can see the, I'll do it in red again. So can we come up with a potential formula for this? I guess you guys need to tell me where the hole is. And the game we want to play here is we want to find a formula of least degree that achieves these patterns. You said 2, 3?
No, 2, 0. Oh.
No, this that. We'll do 2, 3 was good. 2, 3 is fine. We'll say the hole's at 2, 3. All right, let me get us started. So we want something like f of x is equal to okay. So to get a volcano at x equals to -1, I would like a division by x plus 1 squared. All right? Something like that. To get a crossing over here, I need to figure out, where do you guys want to make this point? Pick any point.
I feel like 6.
I heard a 6? 6 it is. So if I want to cross at 6, what do I need to put there? X minus 6. Very good. All right. Now what else do I want? I want a hole at 2, 3. So how do I get that? I do the hole punching that I just talked about in my silly example 7. And I just multiply by x minus 2 over x minus 2. That should punch a hole in it at -2. I've got a y asymptote of y equal to 0. That's good, because I've got degree 3 over a degree 2. Now, there's a flexibility I have in all this, right? I can put whatever number I want up front, right? So what should I choose a to be in order to make the hole go there? See, what I want is my reduced function of 2 to be equal to 3. What is the reduced function here? Well, it's a times 2 minus 6 over 2 plus 1 squared. Like the reduced function, I'll bubble it in green, is this piece right here, right? This would be the reduced function. And so then I can just solve that and pick out the a that I want, and there you go. We have produced the rational function that has the volcano there, has the hole in the graph where we want, crosses the x-intercept that we want. This is reverse engineering my example. So anyway, pretty much all of Wednesday, except for that pesky quiz, which won't take the whole time. We have for your questions about the mission, right? The mission's due when? Friday start of class, not end of class. So I'm collecting it at the start of class Friday, so make sure you're done by then. Thanks, guys.